Okay, well, welcome to another online session of ECE344 microprocessors and a little bit of commentary regarding tests, quizzes, and so on. The quizzes over the lecture materials are posted. There are some deadlines for those, though you can continue doing those to practice after the due date. But the grading will be done at the last submission done before the due date, and so you have many opportunities. My expectation is that all of you would get hundreds on the quiz or 100% of the answers after hopefully one or two tries. And so my objective is for you to actually learn the material. I'm not so much trying to focus on the scores, but this also gives you incentive to do those quizzes. We will have a test on Tuesday, and there will not be a lecture on Tuesday. And what we'll do is we'll cover the material that we've talked about previously. And again, this will be an online test. It is not a time test. So I'm going to release it Tuesday morning, and you will have till Friday noon to complete it. Now, again, I don't want you to wait till Friday morning to start on the quiz or the test, because this is where I usually encounter problems, especially when we have a lot of students. You start and you don't finish before the deadline and so on. So start early. You have 2 submissions possible. The last submission will be graded. As I have another class where we've done something similar, and if you start a submission, you need to finish it, because if you leave it and you decide not to submit it, what happens is Learn keeps the quiz open, and I can't grade any submissions because the test is not submitted. So if you're going to start the second one, you have to go through and finish it. So finish what you start. Okay, so today we're going to talk about the I2C interface. And before we jump into that, are there any questions at this point? And let me just look at. Okay, so you can save and resume, but you must finish it before the deadline. Okay, the deadline is Friday noon. And if you start it before the deadline and you submit it after the deadline, I think you'll be fine. But you must submit it, because when it comes time for me to grade it, I have to have it complete so that I can actually grade it. Okay, so I2C is a topic for today, and we're going to see that it has a number of different ways that it's referred to. I2C, I2C, 2-wire, and those are common names that are all used for the same interface. And we're going to find that it's nice because it's simple for the interconnect. However, that comes with a associated cost. We see on our PIC 32, and we'll just walk around the neighborhood a little bit. We have talked about how we use all of our digital I/O ports. We've talked about using the timers. We will ultimately talk about our pulse width modulation. We may talk about change notification. Input compare, we probably won't mess with. SPI, we just recently completed. And now we're going to, after we do our I2C, we'll start talking about our 10-bit A to D, and we've talked about the UART. And so at this point, we focus on I2C. And we see the characteristics of this interface are that the transmission is synchronous and half duplex. So when we say synchronous, what do we mean when we say synchronous? This would be something that you should know as a little hint. So what do we mean when we say synchronous? And you can type in, you can press your microphone. And I see that we're getting a dearth of answers. And so when we say synchronous, we mean that one of the stations, predominantly the master, is going to transmit a clock. If we say half duplex, it means that we have one station communicating at a time. So this is just like us being in a room where we're all communicating or trying to communicate, but to be able to communicate intelligently, only one party can talk at any given time and everybody else listens. So this is the notion of half duplex communication. Just like if you were talking on a radio and you're sharing the frequency, only one of you can talk at a given time. So because we have this configuration, we are able to do it with just two signal wires, data and clock. And this is a serial transmission, so we transmit 1 bit at a time. So if I look at the actual configuration, I see that I'm going to have a master. Associated with the master is I have my clock, my serial clock and serial data. And associated on the slaves, they also have the same clock and data. So everybody is tied to the same clock and the same data lines. So that's the good news in terms of the electrical connections. However, as we will see, it adds to the protocol complexity. So our specific I2C interface can operate as either a master or a slave. Now, we're going to see when we start looking at this in detail that if I'm going to be a slave, then I have to have an address, because this would be very much equivalent to me communicating to all of you in the room. If I say, okay, Amber, I'm going to send you a message. First thing I have to do is I have to identify you as the recipient of the message, and then we initiate our communication. And once that communication is over, if I want to go to somebody else, then I say, Alan, I'm going to talk to you. I would now use your name and communicate with you. So when we are configured as a slave, we also have to be configured with an address. Now, depending on the number of interfaces I wish to use, or the number of components on this bus configuration, now I'm going to either use 7 or 10-bit addresses. So if I use 7 addresses, then I can address up to 127 items, or 127 different recipients. With 10, I can do 1023. So that would be a very extensive bus configuration. Now, because we want to be able to both send and receive data to our components, we can have bidirectional data transfers. I can either transmit or receive from the master to the slave, and we'll see that we're going to actually be transmitting and receiving from our component. And I can suspend and resume these transfers if I'm doing or using serial clock synchronization. Probably not something that we're really interested in. The other thing is I also have the ability to support multi-master operation. Now, if you had been working in the network, traditional computer network business in the 90s, you would have been very familiar with this, where we had a single shared cable, and now I had multiple computers that were communicating on there simultaneously. And oftentimes when you have remotely located devices communicating on the same medium, you often have that instance of where two stations start communicating simultaneously. It's just like if you are with a group of friends and all of a sudden both of you get a notion to say something and you both say it at the same time. Well, what happens? Well, what happens is you both pause momentarily, and one of you may say, go ahead, or the other one says, no, you go ahead. Well, the way these devices work is they say, all right, we detected that we both are starting to communicate simultaneously. So what we'll do is we'll both wait random periods of time, and then we will try again if we listen first and decide that no one is talking, and then we can talk. So it's called collision sense, so CSMA, collision sense multiple access. And the way you do the collision detection and arbitration is you wait a random amount of time. So we can do that with this I2C interface if we are going to configure the system to have multiple masters. Our applications will be simple in that we will have only one master communicating. The other thing is we can also use address bit masking. So let's say, for example, I want my station to respond to a number of addresses. So I might just respond to one address, or I might respond to a series of addresses. I can use bit masking to be able to allow me to basically respond, if I'm the slave, to multiple addresses. Okay, so what we see here is a little bit more complex kind of configuration, and I'm going to try and zoom in. Okay, and so Well, I'm not going to go through the details at this point, but what I want to show you is that I have a number of registers that are bolded. So notice here I have my I2CX RCV. So this is the register where I will receive data. So I will read from this register to read data that I've received on the I2C interface. So here's our two pins, our serial clock and our serial data. I have a shift register in which the data are shifted, and then they're going to be transferred over to the receive register. Oops. I don't know how I shifted there. Just touched my mouse in it. Okay, the next thing we have here is a mask. So if I'm operating as a slave, I have to have my address. My address is going to continually look at the address that is being transmitted to see whether or not there's a match. And I will use a mask to allow me to be able to, if necessary, respond to multiple addresses. Like most other interfaces, we're going to have some status bits. We want to know, do we have data in buffers? Do we have an empty transmit buffer? And so on. We also have a configuration SFR. And we have a transmit buffer that is basically going to be where we will write data when we wish data to be transmitted over the bus. And like many of our other interfaces that transmit, we are going to also have a baud rate generator register, so we will configure the data rate at which we'll transmit data. And we'll come back to these in a little bit. We start talking about how this actually works. Okay, so one of the things that happens with this I2C communication link is we have two wires, and on these two wires, all of the devices are all connected simultaneously. And at any given time, one of those nodes on the bus is going to be sending signals. So you're probably wondering, well, how do we do that? And you have seen this before, but I want to revisit it so that it hopefully makes a little bit more sense now. Okay, so what I showed you is we have all of these devices connected, and we have all of the signals tied together. So recall when we were looking at our ports, we were looking at our open drain configuration. Well, in this type of communication link, what we have is we have the following kind of configuration. So imagine now if I looked a little deeper into the master block that I have shown here, if I looked at my output, what I have is I have an MOS transistor in an open drain configuration, and I also have it tied to the same line that's tied to the input. So depending on whether I'm reading or writing data, I'm going to be asserting the signal on here, or I'm going to be monitoring this signal to detect what data are being input. And notice if I don't have this connected to anything, this input here and output are floating. So what I have to do is I have to use a pull-up resistor. And so this resistor here is going to pull up those signal lines to the supply voltage, VDD, which will be about 3.3 volts, and same thing on the slaves. So I have these output transistors that are tied together, and they're also tied to all the inputs. So I have all that circuitry tied together, and now I need to be able to, at any given time, be able to write data or read data, and it all has to be orchestrated so that we have reliable communication. So let's look a little deeper into how that actually happens. So multiple devices can assert that signal on that shared line, inputs and outputs, all simultaneously. Now recall on SPI, we used a slave select, an explicit signal that we could actually identify each slave, and so we could, when I was going to talk to a slave, I could assert that signal so that the appropriate slave would respond accordingly. Well, in this case, we're going to transmit an address on that data line so that we can detect or we can determine who should be sending or receiving data in that transmission. And so we're going to see that there's also some little tricks in there. So first thing I want to mention is in our configurations, we're going to use 7-bit addresses. Okay, so we're going to look at a signal and we'll see how that actually works. Okay, so what we have to do first is we have to determine when is a good time to be able to send data. And so you will see as we actually look at code implementations, there are many calls to functions to determine whether or not the bus is busy. And the way we can determine if the bus is busy is I will look at both the clock and the data lines, and if they're both high for some finite period of time, I know the bus is idle. And so we'll see that we actually have an idle call to determine that, in fact, that the bus is idle. And then we have a start bit. This start bit is different from our UART. This is basically going to be identified by a transition rather than a bit time. And this is a very specific high to low transition, so the data line is going to make the transition when the clock is still in its idle mode. And then we're going to use the clock pulses to actually transfer data. And so you see there's a couple rules here. So the data on the bus has to be stable during the period of time when the clock is high, and we'll change the bits, individual bits, during the time that the clock is low. And there will be acknowledgments between the slave and the masters, the master and the slaves, I should say, whenever there's a transmission of 8 bits. And we'll see that this is going to be done by whoever the recipient is, basically keeping the data line or lowering the data line during the acknowledgement clock pulse. So let's look at how this is, there's also another signal that we have to do to indicate this is the end of the message. And so when the end of the message is complete, then the master is going to basically go through an end of data indication by basically doing a negative acknowledgement during the acknowledgement time, and then it's going to do what is called a stop bit, and this is going to be a low to high transition of the data line when the clock line's high. So let's look at an example of this. Okay, so I'm going to zoom in a little bit here in a second, but first let's just look at what happens. We have a start, and the start is generated by the master. Then the master is going to transmit data to the slave. The slave is going to acknowledge by basically pulling this output line low. In this case, now it's the master that's asserting the signal. And so notice this line here indicates the period of time that the master is actually asserting a signal on this lower line. Then during this time interval, it's the slave that's doing the acknowledgement. So it's asserting the signal. And then now the master is going to send data. Well, in this case, I'm reading from the slave. And so there's also something encoded in here, which I'll mention in a second. So in this case, this is now data coming from the slave to the master. So now this is the slave asserting signals on the line. Meanwhile, the master is the one generating all the clocks. And then we have an acknowledgement. Then I send more data. And then the master is going to do a negative acknowledgement. And then we do our stop. So let's move in a little closer here. Okay, so here my clock is idle. And while the clock signal is high, the master brings the data line from high to low. And that's the acknowledgement, that transition from high to low. Now, then I start sending data, and I send, notice there's 1, 2, 3, do it up here, 4, 5, 6, 7, 8, and then the 9th clock phase. So there's 8 data bits, and then an acknowledgement clock, during which time, so the slave has received these data bits, and now it keeps that line low think there's a time interval in there because I didn't touch anything. Okay, so the slave holds the line low for that time duration. Then there's a slight pause, and now notice here's 1, 2, 3, 4, 5, 6, 7, 8. So now the slave is asserting the data line on the lower display. There's a little bit of time, and now notice here's an acknowledgement clock, and this is the master now pulling this line low. There's more data to follow, so these are data bits. So this is now the master again. This is slave asserting data, and these are clock bits. So notice there's 4, 6, 7, 8. So now this is the, sorry for the zoom in, zoom out time. It's the, so I have 8 data bits, and there's a little period of time here. So now the master, this is the end of the transmission. It had requested 2 bytes, or it was expecting 2 bytes, and now it is doing a negative acknowledgement saying, okay, I received the data, and now what I'm going to do is say this is the end of the transmission. This is the master. So now the data line is low, the clock goes high, and the master brings the data line from low to high, indicating the stop of the transmission. So the essence of this is the simplicity of our electrical interconnection has now resulted in a protocol, a communication protocol that is considerably more complex. And you can imagine if you're designing circuitry that is going to actually implement this interface, there is some very close orchestration between the clock and the slaves to ensure that all this timing is done properly so that the signals work reliably. Okay, so now let's talk about using these actual interfaces on our hardware. So we see that we have 5 interfaces on the PIC32 microcontroller. And now the next question is we want to use them on the MX7. So we come over here to our MX7 reference manual, and we examine our I2C interface, and we see that we can use J7 and J8 for our I2C1 and I2C2. And before you wonder too much where J7 and J8 are, let me do this. And I'm going to zoom in again. Hopefully the system will cooperate for a while. So if you look closely, you see that we have these 2 connectors, and recall these are bus interconnects, and so I can have multiple connections to this I2C connector. So one is I2C1, the other is I2C2. And what we're going to do is we're going to use I2C, and I'll have to go back to the page there. But we're going to use it, and there are also connections here, so you can read this I2C pull-ups. So in some configurations or some peripherals, we will have devices that will have built-in pull-ups, and there will be situations of where I need these pull-ups because none of the devices have pull-ups, and there will be other situations of where I don't need them on the MX7 because the peripheral devices also have pull-up capability. And so what we're going to do is we're going to use, or we will use in the videos and in our demonstrations, we're going to use these connectors, and we're actually going to use our 6-pin connectors with 2 pins hanging off on the far end so that we can connect to our devices. So let's come back over here and see that. Now, one of the things that is also characteristic of the MX7 is it has some onboard I2C devices. And in fact, I2C2, let's see if I have that highlighted. So we have an onboard EEPROM that is also tied to the I2C. And so what we're going to do is we're going to use I2C1, and we also have the pull-up resistors using JP3 and JP4 that work in conjunction with connector J7. So we see that we have two that are easily usable. We also can access two others using our PMOD connectors, but we're going to focus on using J1 and J2, or IC1, IC2, and we'll use specifically IC1 because IC2 is also tied to an onboard EEPROM. And so this makes life a little easier for us because we have no ability to change the address on the EEPROM, and as I recall, it conflicts with the address that we use on our device. Okay, so coming back to this, we say, all right, we're going to use I2C1. And as I mentioned, I already just mentioned that we have the E2PROM tied to I2C2. And we can access the others on our PMOD connectors. Not quite as convenient. Okay, so let's look at the SFRs. And I'm going to zoom in again. We'll go to the data sheet and get a little bit more detail here in a second. Okay, so recall we looked at a number of the, let's look at I2C1. And we see that the address again is BF80, and the first one is BF805300. This is our configuration. Here's our status. Here's our address mask, a baud rate generator, transmit buffer, and receive buffer. So we see we have a few more SFRs than what we had previously. Okay. Now, what I'd like to do is I'd like to also talk about the device to which we're going to connect. Okay, so we're going to actually communicate with a temperature reference manual. And this temperature reference manual basically also, well, it communicates also using I2C, and we're going to see characteristics of it, and we'll get a little bit more detail of the characteristics. But what we want to do is we want to understand a little bit of how we actually will connect it to the MX7. So first thing I draw your attention to is notice we have selectable addresses. And that's going to be important because when we start communicating with it, we have to embed those addresses in our commands to the temperature module. And so first thing we want to do is we see that this uses our I2C, so it has similar 4-pin connectors as what we have on our MX7 board. So that's why we can use the same connectors, and next time we'll actually run it and show you live operation with it, but this time we want to talk about how we actually use it. So first thing we have to do is we have to connect the devices together. So that's the electrical connection, which is the easiest of everything. And now we say, all right, we're also going to have to, if necessary, use our pull-up resistors on this device. So we can either connect JP4 and JP5, which are pull-ups, and we also have a temperature alarm capability in here that we're not going to use for our purposes, but we have that capability as well. So next thing we have to do is we have to set up the addresses. Now recall we have up to 127 possible addresses using 7 bits, and what we're going to do is we're going to use a very limited subset of those, and these are the address options that we have. And so the way we do that is we basically configure these 3 jumpers to give us one of 8 possible addresses. And so we will pick one of these addresses and configure the jumpers appropriately so that we can actually extract data from this temperature sensor. Now we also have to send it some information to configure it to select the appropriate output, and fortuitously, or not fortuitously, unfortunately, this reference manual, which you see, this is 3 pages. This is the extent of the documentation that we get for the device. However, we also have some information about the components, and so by doing a little further research, we can actually determine what commands we might need to send to this device to be able to allow us to use it in the way that we'd like to. Okay, so let's talk a little bit about configuring this device. So as always, first thing we want to do is we want to come over here to our, let's go to the data sheet first. This is the reference manual, and let's go to the PIC data sheet. So in section 19 of the PIC data sheet, we see that we have a description of our device, pretty much what we've talked about before. And let's talk a little bit about how this works. Okay, so we have our same clock as we had before, and we see that there is a remarkable similarity to our SPI in that we are shifting data using the clock into a shift register. And we're shifting data into the least significant bit for our receiving data. And when we transmit data, we're going to do the same thing. We have a shift clock, and we're going to now use our device here to shift it into the, so we're going to shift it into the, let's see, my transmit. So I'm going to shift it out of the shift register in a manner what I do before. So I preload the shift register, and then I shift the data out to the data line as appropriate. Okay, so if the addresses match, then I will actually shift the data into the shift register. So I have an enable function on the shift register depending on address. And I also have circuitry that is going to allow me to detect the start and stop. This is important because now I have to preload the shift register or configure it as appropriate. And I need to also generate my acknowledge bit. I also need to detect whether or not there's collision, and I may need to do some clock stretching as well. So we see that the process is a little bit more complex than it was with the SPI. So again, I repeat that the electrical connection of just using two wires makes life easy for the electrical connection, but now the implementation of the actual interface circuitry is a little more complex because we've traded off hardware for this operational, the connection hardware for the protocol implementation circuitry. Okay, so then we say, all right, these are the things that we need to configure. And we're going to go through a similar exercise as before. And we'll see that, of course, we have to enable the device, and we have a number of options. And what I'm going to do is I'm going to go to an example code, and then what we're going to do is in the next lecture we'll talk a little bit more in detail of the actual configuration. So let's look at an example code of how we would actually use this. And so what we're doing here is we're communicating with the temperature 3 TMP3 temperature module. And as usual, we have our same configuration for our clock. And the first thing we encounter is this baud rate generator value. Now, the first thing that we have to do is we say, all right, how are we going to configure this baud rate generator? And so when I look at my reference manual, as I did before, I see that I want to come up with a value that I need to put in the register. And with a little searching, I should have had this on the actual page there. We see that we have a peripheral bus clock of 10 megahertz. And we're going to find that we have to configure it so that we can actually work compatibly with our device. And so we see that we have these frequencies that we can use for our baud rate generator. Now, one of the things that we have to go back to is our peripheral device, TMP. And in the TMP module, or maybe it's in the, I think it's back in the data sheet where it gives us the clock frequencies that we can support. And so what we see is we have two options with our operation of our SPI, either 400 kilohertz or 100 kilohertz. And see we have the value of 9 hexadecimal or 2F for 100 kilohertz. And what we'll do is we will use that value in our baud rate generator value. So we see that we're using the value of 9, which would correspond to the 100 kilohertz frequency. Now what we do next is we say, all right, I'm going to I have a buffer here, and I'm going to open my I2C, very similar to what we do before, what we have done with our other devices. And what I do is I go over here to my peripheral library for the SPI, or I'm sorry, for I2C, and we see that we have our open function, and we have the options here of which we'll go through in a little more detail next time. But what I'm trying to, in this discussion today, is give you a preliminary insight into the code is going to be a little bit more complex because we now have to take into account the timing operations. So I open my device, I configured the slave address, I put that into my buffer, and I'm going to do a shift register because I'm going to actually write. So we use 7 address bits, and we use the 8th bit to indicate to the slave device, is this going to be a read or write operation? And so what we do is we take the slave address, shift it left 1 position, and now we append it with a 0. So we end it with 0, saying we're going to set that bit as a write bit. And we're going to write this value, which in this case is setting a register on the temperature module. We indicate that we have 2 characters that we're going to transmit, the address and the actual data. We start the I2C, so this is sending the start bit, and then we have an idle function to ensure that now the bus is idle. Then we write, so now the I2C interface is being directed to write 2 data bits. So we're going to write them one at a time. So we say while data size, so we're using our data size as 2, and we're decrementing it during the loop. So we write a character, and we wait for the bus to be idle. Then we write another character and wait for the bus to be idle. And if we send it out successfully, we get the acknowledgement, then we will basically stop that loop and break out of that loop. So, and then we stop and idle. So you see that this is just for a very simple sending out a command. The software implementation is a little bit more complex. Similarly, when we want to write data, in this case we're going to be reading data. Now we're going to be reading temperatures. So first thing we do is we will restart the bus. And so you see it's sending the stop condition. And then we wait for the bus to be ready or idle. Then we do a master write, again our slave address. In this case we're ORing it with a 1. So we want to make sure the least significant bit is always going to be 1. And we wait for that to be idle. And then we now are going to read from the I2C. We're reading in 2 characters, and this 152 is a timing parameter, which we'll see a little bit later. And then I stop, wait for the bus to be idle. So I've completed my I2C communication, and now I convert the data that I've read. I've read 2 bytes, and now I convert this to a temperature. And we will actually show this operational in the next operation. So one of the things that I'd like you to appreciate is the fact that using the I2C is a little bit more complex. And the reason it's more complex is because we have to support this protocol that requires acknowledgments, timing, and so on. Whereas with SPI, it was a very simple kind of transaction. In this case, the I2C is a little bit more complex. The good news is once you have this configuration, then it's reasonably straightforward to actually implement. Now, you're probably wondering, well, how did I figure out all of these different idle conditions and so on? Well, this is where we want to draw on the resources we have at our disposal. And in this case, if I come back and I'm going to looking at I2C, and I look at examples of use. And so this example of use basically gives you good insight into how you can actually use this, and this shows you a number of idle function calls and so on. And so this was where I basically figured out where I had to actually implement the idles and so on. So this is an example provided by Microchip in their peripheral library that basically gives you some insight into how to actually configure this. In this case, what we're doing is we're communicating with the onboard EEPROM, but it is exactly the same thing when we communicate with other I2C devices. Okay, so what I'd like to do is, at this point, just, I don't know why it didn't resort back to its normal size. What we're going to do next time is we're actually going to walk through the configuration and the code and the operation of this, and we'll monitor the execution with the oscilloscope to see how this data transaction is actually taking place. But I'm hoping that you start to see that we have traded off a very simple interconnect hardware-wise for a complex protocol that is necessary, because now we need to identify, when we have a bus structure, how each one of these devices is going to respond, and we see that it adds a lot more complexity to the system. And so it is a simple interface once you have the protocol and the timing established. But getting that done properly, because of the complexity of this interconnect protocol and the fact that you have many potential stations asserting signals on this particular line at any given time, makes the system a little bit more complex. But I'm hoping that once you start to see it work and you get some confidence working this, you will see that the I2C is indeed an attractive communication interface because of its simplicity in terms of the interconnect. So we'll leave it there for now. Any questions on this communication interface and its protocol at this point?
Hey, Dr. Nava. So when you have actually this graph that you have up right here, are you always going to send 8 bits, and that's how the slave knows that it's still receiving data versus, say, end of end of transmission sequence?
So in every transaction, every transmission, the very first 8 bits are going to be a 7-bit address and then the 8th bit will be configured to indicate whether it's going to be read or write. And so when I do that, I will always start a transmission with an address and indicating whether it's going to be read or write. And then what will follow will be either the master or the slave transmitting data. Because this is half duplex, it can only be one direction at a time. So it can either be the master sending and directing, so indicating to the slave that I'm going to send you data, so be ready to accept data, and after the appropriate number of bytes, then so in this case, if let's say that I'm right, in this case I'm reading, okay? So in this case I'm sending the address, the 8th bit indicates read. so this acknowledgement is the slave saying, okay, I acknowledge the address, and now I'm going to send you data. So now the slave sends data, and that's why you see this little timing gap, because I'm waiting for the master. Well, and it would be the same if it was the slave. I'm waiting for the recipient to acknowledge, whether it's the master receiving or the slave. In this case, it's the master receiving, so he acknowledges. And then the next 8 bits are transmitted, and because that's what the master expects is 2 bytes, it's going to send a negative acknowledgement saying that's the end of the transmission. And then it will send the stop indicating that it is going to, that the bus will now be idle.
Got it. Thank you.
So you see, and the thing that's a little bit complicated is I have to be very sure that I understand who is supposed to be transmitting when I do read or write. So I need to look at this 8th bit, which is this one right here, right where the cursor is. The next one is the acknowledgement by the slave. So at this one, this indicates, because it's a 1, it indicates that this is going to be a read from the slave. And if it was a 0, it's going to say this is a write to the slave. And so then the acknowledgement will be asserted by the slave instead of the master. And so you can see the complexity. I can't just look at the signal without being a little bit more observant in terms of, is this a read or write observation? And so remember, our addresses were, what were the addresses on our, we'll have to look at the code, but it looks like an F, and then maybe, so I have 1, 2, 3, 4. Let's see what the addresses are, just for grins. Okay. So it looks like I have a 1. So I have a 1, 1, 0, 0, and then all ones. So that first one, coming back to this, and notice what I'm doing is I'm seeing the most significant bit first. So I have a 1 for a read. I have 4 ones for the address, and then 0, 1, 0, 0, 1. And so this correlates with what we saw on the address. And then the rest are data. So I have to look at the zoom in to get the 1s and 0s for those. But the protocol is a little bit more complex because of I have all of these devices that are potentially asserting a low on that line at any given time. Okay, so next time we'll do is we'll actually get into the configuration of it, and we'll actually see this operation live. We'll have the temperature module functioning, and we'll look at configuring the SFRs and the options that we may choose to use when we deploy this I2C interface. Now, the good news is we'll use it in a simple configuration, but we could use it in any number of complex configurations as well. And this is characteristic of virtually all of the interfaces, is they have so many options that configuring it can look a little bit intimidating, but for the most part, we only need to select a subset of them to use it effectively for our purposes. Okay, any other questions? But don't be intimidated by it. Once we get it running, we'll see that it actually works very, very well. But it is a little more complex. Okay, well, I'm going to stop the recording if there's no other questions. So again, a reminder, we'll have an online test. It will be available to you Tuesday morning, and you will have until Saturday at 10 o'clock to complete it. You will have 2 attempts, 2 submission attempts, and it has to be submitted by the deadline.
I have a question.
Okay.
So can you talk about the format of the test, please? So is it going to be similar to the last test, or it's going to be similar to the quizzes?
I'm sorry, I didn't get your question there.
What is the format of our test, of our coming test?
The format of the test will be that you will actually type in textual answers. There might be some where you actually might be a few multiple choice. It'll be more like the first test that you took rather than the quizzes.
Can we print the question and scan it back or no?
I think I would rather you just type them in. You shouldn't have to, because you have 2 attempts, so you can look at it and you'll see the same questions. It might be different order, but you can look at the test if there's something that you're not quite clear on.
Okay. Thank you.
You're welcome. I don't think Learn will let you in the test mode scan in those or paste in scans. You may be able to. Students are very creative in terms of how they submit things. That's a compliment. Any other questions? Okay, well, I should be posting some more lab videos on the weekend, and so we'll look at how we use the SPI in, or not, sorry, SPI, how we use I2C in real-world applications. Okay, well, I'm going to stop the recording, and I will look forward to seeing you after the test. And if there's any questions, please email me, and let's keep this ball rolling and keep smiling. Thank you. Thank you.